Hello everyone, my name is Rohit Singhal and we were discussing about the topic hydrocarbons. In the previous classes I have studied with the aromatic hydrocarbons and I have discussed a few things about it, and in this class and the other onwards we will discuss more in the detail. So, let us start with it. We were discussing aromatic hydrocarbons. Let us actually summarize a bit what we have studied till now is we have studied first thing is two forms of aromatic hydrocarbons. One is benzenoid, another is non-benzenoid. Example is benzene, naphthalene. Benzenoid forms matlab that contains the benzene ring, and non-benzenoid example are pyrrole, furan, etc. Second thing we have studied is molecular formula of benzene. We have studied details in the benzene. So, benzene what we have discussed, molecular formula is C6H6, that means 6 CC sigma bonds present, 6 CC CH sigma bonds present. The CC sigma bonds contain bond length of 139 picometer, and it is actually the intermediate of normal CC and C double bond C. Okay. So, these things we have studied. Gives substitution, it undergoes substitution rather than addition, unlike alkenes. So, this is different from this. Okay. Faraday isolated in 1825, and later on Kekulé proposed two canonical forms or two canonical forms of, or we can say isomer forms of it, and those are and he suggested that both of the forms can be equally possible, A or B. Later on what we have got that VBT explained the stability in benzene, and the stability in benzene is due to the resonance happening in it, and then VBT came out with the idea that these two canonical forms can be represented in a one hybrid form, that is called resonance hybrid, that can be represented by like this, and these are called the resonance hybrid. So, VBT suggests the stability in the benzene. Then we moved further towards the structure of it. Structure and bonding we were studying, and what we have got is all the carbons are sp2 hybridized, all the carbons are sp2 hybridized, and sp2 hybridized contains 3 sp2 hybridized orbital and it has 1 sp2 unhybridized orbital, or it has, you can say, 1 unhybridized orbital. Among these 3 sp2 hybridized orbitals, 2 sp2s are involved in 2 CC sigma bonds with adjacent carbon and 1 sp2 involved in CH sigma bond. Till this point we have discussed the things, and now starting forward we have also drawn the structure then, and the structure was like this. Okay, what we have, okay, these 6 CC bonds have been used by one carbon is using the 2 sp2 hybridized orbital to make 2 sigma bonds with its neighboring CC. Okay. If I am talking about this one carbon is making 2 sigma bonds with the using the 2 sp2 hybridized orbitals. Okay. So, now what is happening is, and the one is using the to make the CH sigma bond. Okay. So, now this after making this 6 sigma bonds, after making this 6 CC sigma bonds and 6 CH sigma bonds, now what we have left with is one unhybridized orbital, unhybridized p orbital is there. So, this unhybridized p orbital is perpendicular to each other. This unhybridized p orbital is perpendicular to adjacent carbon orbital. Okay. Similarly, these ones are present. So, what happens is this pi bond it makes. So, we can show like this. Okay. So, what we have got the structure of it is C. Okay. These are the H, or in simple, if I am representing this carbon as dots, the structure can be written as like this. Okay. The other canonical form can be represented by the other way. Similarly, there are C, there is hydrogens, it makes double bond with the side ones. Okay, and we will get the structure like this, and this is the another canonical form of what we have discussed of the benzene. Two canonical forms are present, that means alternate pi sigma bonds, and this pi how these pi sigma bonds, 3 sp2 hybridized orbital, 2 are involved in making CC sigma bond with the 2 adjacent carbons, 1 is involved in making the CH sigma bond, and remaining the unhybridized p orbital is involved in the pi bonding, that is orientically aligned perpendicularly to the another adjacent p orbital of the carbon, and that can make a pi bond, and this will be the structure of benzene. Then moving on to the further, that I have already discussed about the CC bond lengths are there, C double bond C bond length. Okay. So, what about the canonical form? What about the canonical forms we have discussed? If I will talk about the resonance hybrid, so this can be shown by this diagram as like this. Okay. So, how this pi bond or pi electron density is resonating in the hybrid form is like we can show it like this. Similarly, this lower ones are also. Okay. So, you must be saying that what is what actually you can see is all kind of a ring kind of structure it is. So, you must be saying this pi bond is actually making a fencing and this ring is inside and the electron density, this whatever is shown is by this dash is actually the electron density that is circulating in the entire ring. Okay. So, this ring kind structure. The circular ring represents the delocalization of pi electrons, and this delocalization means that the electron density, the pi electron density is circulating in the entire ring, that is pi electron density entire ring. And this what you might be saying is this like a kind of also represented as a donut like structure. Okay, two rings upside and downwards are present, and in between there lies the this ring. Okay. So, the electron density, electron cloud okay. So, kind of इसको सर कट करना थोड़ा सा, ठीक है, जब ये पार्ट हुआ है वो हो जाएगा ना. And this ring kind, this hybrid can also be can be shown as the donut like structure, where this ring, this electron cloud is shown as the electron cloud can be shown as two donuts or two rings like which we have shown, and in between exists a this benzene structure. Okay, and this electron cloud density can be represented by the ring structure, is called the donuts kind of something. Okay. So, these 6 pi electrons are delocalized over the entire ring. So, this was about the structure of benzene, and now we will discuss about its properties and synthetic procedures and how it is different in reactivity unlike the alkenes. Okay. It also contains the 3 double bonds, but how it differs now with the reactivity. We know why the reason why it will be differing with the reactivity. Now, we will see what are the reactivity difference between the alkene and this, and we will also see the isomerization and further things of benzene and its similar structures of aromatic hydrocarbons. So, till now we have discussed briefly about the structure and bonding of the aromatic hydrocarbons. We have discussed about the benzene, we have discussed about basic structure of benzene. We have discussed there are two forms present, benzenoid, non-benzenoid. discuss few things about benzene, how Kekulé proposed the structure of it, then VBT gives the canonical or the hybrid form of it, and discuss why how the bonding can be described by using the hybridized or VBT thing, that there are two sp2 hybridized orbitals involved in CC sigma bond, one is involved in CH sigma bond, and remaining unhybridized p orbital is involved in the pi bond formation with the adjacent carbon. This pi electron density is represented, can be represented by the this ring kind of structure also, that can be shown by the donut structure also. So, this is how we have formed the two canonical forms of benzene. The resonance or hybrid form is represented by the VBT or been explained by the valence bond theory, that is VBT. In further classes, we will discuss about why, how these hydrocarbons, how they can be synthesized in the laboratories, how these reactivities different from the alkenes moieties, and some basic physical properties also, that we will discuss in the upcoming classes. Thank you.